In exercise 9.13, we are going to show that for all x a or b is a logical consequence of for all x a for all x b. And then we are going to give a counterexample demonstrating that the opposite implication, so that that this is a logical consequence of this, is not true, so it doesn't hold. So, if we remember from exercise 9.9, that this is a logical consequence of this means that sort of for all x a or for all x b implies for all x a or b is valid. So it's a tautology essentially. So this is by definition 9.23. If f is a logical consequence of g, then g implies f is valid. So we'll just rewrite what we're going to show. So by definition 9.23, we have gone from this line to this line. And now we can further rewrite it by just changing up the implications a bit. We move this to the front and this to the back, and then put a negation in front, so that we have negation of for all x a or b implies negation of for all x a or for all x b. And then now we can push this implication in, so to speak, so that we get an existence quantifier, and then the negation is in front of the a or b. So this is this rule right here, which we've just used. So now we're going to go ahead like last time and try to show that this is true, so that that this implication holds. So if this implication holds, it means that there's some we assume some arbitrary m structure m and assignment v, such that this first part here, so that this part here is valid, or is satisfied under this structure. If it's so that existence x negation of a or b is satisfied under M, then that means there is some a in M such that the negation of a or b where x is evaluated is assigned to a is true. So now we've handled the quantifier here. And now by De Morgan's, this is true if and only if this here is true, so the negation of a and the negation of b under M and v is true, or is evaluated to 1. And then this again is true if and only if the negation of a is evaluated to 1 and the negation of b is evaluated to 1. So then again, the fact that negation of a is evaluated to 1 and negation of b evaluated to 1 implies that, okay, and there's a little mistake, it implies that the existence x such that the negation of a and the negation of b here, these are two different x's, separate because they're separate quantifiers, but yeah, they mean the same thing, that these are evaluated to 1. So that so it is true that we have an existence x negation of a and the same for b, so these are both true, and that means that if we just move this negation out, that it's not true that for all x a and it's not true that for all x b under M and v. And this again by De Morgan's equals that the negation of for all x a or for all x b is also true. So now we've reached that this here is true based on the assumption that this is valid under some arbitrary M and v. And since this is true, it must be under the structure M and V. It is satisfied under M. So, since it's satisfied under M, we can have that existence x negation a or b implies negation of for all x a for all x b is also satisfied under M and V. And remember, we said that M and V were arbitrary up here. And since they are arbitrary, this formula is valid, and the logical consequence holds. So that was showing that for all x a or b is a logical consequence of for all x a or for all x b. So I've just shown this here. But now we're going to give a counterexample demonstrating that the opposite implication doesn't hold. Okay, I'm just going to get rid of some stuff here. Yeah, I can get rid of that. Okay, so what do we need to do to show that it doesn't hold? Well, we need to come with some sort of a counterexample. So what counterexample could we take? Or like what structure could we create such that this is true, but this isn't true? Because we'll be doing the same thing. We have to show that that this implies this is not a tautology. So here we have for all x, a or b is true. So either a is true or b is true for every single x. But here we have that a is true for every x and b is true for every x. So now we just need to create some kind of a structure and an interpretation in which it's always true that either a or b are true, but it's not always true that a is true, and it's not always true that b is true. So both of these have to be false. So the example that they've got in the solutions here is we're going to let m, so the structure m be defined as the natural numbers, and then we're going to let the formula a be the unary predicates e, and b be the unary predicate o. So this is just, think of it as even for e and o for odd. Yeah, so e and o are unary relations, and they're defined such that n in the natural numbers is in e if n is even, and n from the natural numbers is in o if n is odd. So evidently this is true for the first part, because for every natural number, either a is true, so either the number is even or the number is odd. So the number will always be either even or odd, but it is definitely not true that every number will be even, and it is also not true that every number will be odd. So then we'll have something true implying something false, which is again false, and therefore the implication in the opposite direction doesn't hold.